Welcome, this is Mr. Ensler, and I'm going to go over the Geometry Chapter 2 review. So we started off this unit talking about patterns, and in number 1 we have a pattern here. It says sketch the next figure in the pattern. And so I can see we start off with a square. We still have a square in the second one, but it's split down the middle. In the third one we still have a square, but then it's been split again. So I predict that the fourth one is going to be a square. That's my best shot at drawing a square freehand. And we're going to split that last shape down the middle, and so the shaded area will just be this vertical section there. So it's like if we split this right here and then only shaded in that area. Okay, on to number 2. Let's see here, what's going on with this pattern? We have 1 dot, then 4 dots, then 9 dots. So those are all perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, so I predict next we're going to have 4 squared is 16. So I think I'm going to have a square of 16 dots, 4 rows of 4. It didn't say you had to describe the pattern here, but you can describe it any number of ways. If you want to say these are all squares, this is 1 by 1, 2 by 2, 3 by 3, and the one that we're going to draw should be 4 by 4. Alright, now these ones we're going to write the next 3 and describe the pattern. When you're looking for a pattern, start with the most basic of things. Is it going up? Is it going down? I can see this one, number 3, is going up. Is it adding something each time? Well, here it adds 1, then it adds 2. This is where a lot of people give up and they say, oh, it's not adding the same thing each time, so let me look for another thing. But I suggest just going all the way because look, there it adds 3, and I think that's the pattern. It adds 1 more, so I'll say this adds 1 more than the previous time. Or just than the previous. So the next 3 patterns, if I add 4, I'll get 10. If I add 5, I'll get 15. If I add 6, I'll get 21. Number 4. Alright, what's going on here? I can see it's going up. Is it adding something? Well, here it adds 0, then it adds 3, then it adds 12, then it adds 72 minus 18. Let me get out my calculator here. That's 54. I don't really see something there. Okay. Is it multiplying? Let's see, is it multiplying? Well, first it would multiply by 1. Then it multiplies by 2. 6 times 3 equals 18. Does 18 times 4 equal 72? Yeah, it does. So, I think that's the pattern. It's multiplying by 1 more each time. Multiply by 1 more each time. So, I'm going to take 72 and multiply it by 5. 72 times 5 is 360. And then we're going to multiply that by 6. And I get 2,160. And I got to do one more, multiply that by 7. And I get 15,120. 15,120, all right. All right, here we're coming up with a counterexample to disprove the conjecture. We're going to sketch a counterexample. So number 5, regular polygons always have an even number of sides. In Chapter 1, we learned that a regular polygon is a polygon that is both equilateral and equiangular. And so they're saying it always has an even number of sides. Well, that's not true. You can have a regular polygon that's a triangle, for instance. So I could draw that. That's my best attempt at drawing a regular triangle where all 3 angles are the same and all 3 sides are the same. There, that disproves it. That does not have an even number of sides. Number 6, the value of x squared is always greater than the value of x. Okay, let's just kind of explore this a little bit. X squared and x. So let's say x is 5. Then x squared would be 25. Okay, well that seems to be true. Let's say x is 10. Well, let's see here. 10 squared is 100. What if I continued on doing this? What if I put in a negative 4? Well, that squared 16. This seems to be true so far, but the directions say come up with a counterexample. So I need to prove this false. I've used whole numbers that are positive, negatives. Maybe I should use a decimal number. How about 0.5? Alright, so then if I square 0.5, 0.5 squared is 0.25. Hey, there we are. X squared in this case is actually less than x. So that's going to be my counterexample. If x equals 0.5, I suppose that's not really a sketch, but it's a counterexample nonetheless. All right, number 7, all intersecting planes form right angles. Now this is what we see most of the time, but it would not have to be that way. So let's say I have a flat plane like that, and then I'm going to have a plane that crosses through that, but it's not going to cross through it straight up and down. I'm going to have it cross through at an angle. So here's my plane, it's going to cross through there, and it goes through at an angle. Again, I'm not grading your artistry, but you should be able to get your idea across. Supplementary angles always form a linear pair. So supplementary angles are angles that add up to 180, and that's true of a linear pair, but can you think of an example of angles that add up to 180 that aren't a linear pair? Well, how about this? What if I have well, let's say that's a 110 degree angle here, and over here I have a 70 degree angle. Those are supplementary because they add up to 180, but they're not a linear pair because linear pairs are when they're like right next to each other. So there's my counterexample. Okay, number 9. Michael has more money than Alice. Sarah has less money than Michael. Alice has more money than Peter. Jenny has the most of all. As best as you can, rank them in order. Okay, so this is using deductive reasoning, like law of detachment, law of syllogism. Let's rank them in order. So I'm going to take each one of these statements. Starting at the beginning. Michael has more money than Alice. So Michael greater than Alice. I'm just kind of brainstorming here. Sarah has less than Michael. Sarah has less than Michael. Alice has more than Peter. Alice has more than Peter. And Jenny has the most of all. So Jenny has the most, says rank them in order from most to least. Okay, well Jenny's going to come first then, right? Because it clearly says she has the most of all. Let's look at our other statements here. Michael has more than Alice. Michael also has more than Sarah. And Alice has more than Peter. So if Alice has more than Peter and Michael has more than Alice, Michael's going to come next. Okay. So Michael has more than Alice. Alice has more than Peter. Michael has more than Sarah. Well, what we don't know here is where Sarah comes into play. I do know that Michael has more than Alice, and Alice has more than Peter. So, since the only thing we know about Sarah is that she has less than Michael, and we don't know where Sarah is compared to Alice or Peter, since she has less than Michael, we know she's going to be less than Jenny. What I'm going to do is I'm just going to put Sarah's name here, because we know she has less than Michael, but we don't know if she has less or more than Alice and Peter. So, there we go, that's my answer. Alright, write the given statement in if-then form. Band members are musicians, so if you are a band member, then you are a musician. Usually we're going to just keep the sentence in the order that it's in, unless there's some key word that tells us it's actually in reverse order. So, number 11, the sum of two positive numbers is positive. Okay, so if you add two positive numbers, the sum will be positive. So with that one, it originally said the sum of two positive numbers is positive. The way I take that to mean is that you start with two positive numbers and you end up with a sum. I think that's the way that most people would read that, so that's why I put it in that order. Alright, two planes intersect at one line. Again, we can just do this right in order. So if two planes intersect, then, make sure you actually use the words if and then they intersect at one line. And I apologize for my handwriting there. I'm writing on a tablet and it's not the easiest. Okay, number 13, excuse me. Three non-collinear points make a unique plane. So, if there are three non-collinear points, then they make a unique plane. What we mean by unique there is that if you have three non-collinear points, there's only one possible plane that could be made from those. Alright, number 14, in an equilateral polygon, all sides are congruent. So this one will go in order too. If a polygon is equilateral, then all sides are congruent. Alright, great. On to the next page. Okay, on to this next section. We're writing the various forms of this statement. Calculus students are good at math. And the first one is just to write it in regular if-then form. So you just state the thing that comes first, that's the if, the hypothesis, and then the thing that comes after that is the conclusion. So calculus students. So that's the first thing. If a student is in calculus, then he or she is good at math. And although it doesn't say so on here, sometimes we say whether that's true or false, and I think we'd have to agree that that's true. If you have someone in calculus, then they're going to be good at math. Alright, the converse is when you just take the first part and the second part and you reverse them. There's no negatives, there's no negation, you just reverse them. So this would be, if a student is good at math, then he or she is in calculus. So there it is written out. And let's see here, if a student's good at math, then they're in calculus. No, because I have plenty of good geometry students who are good at math, but they're not in calculus. So we're going to say that is false. Alright, for the inverse is going to keep the hypothesis and conclusion in the same order as the if-then. If-then inverse. They both begin with the same type of sound there. So it's going to be, if a student's good at calculus, then he or she's good at math, but with the inverse we're going to add negation. So if a student is not good at calculus, then he or she is not good at math. So that's the inverse, and it will always mean the same thing as the converse. The converse and the inverse always have the same meaning. So if the converse is false, the inverse is basically saying the same meaning, so that's going to be false also. Alright, last up is the contrapositive. This is the one that changes everything. It's going to take the original if-then form and reverse it like the converse, but it's also going to negate it like the inverse. So it's kind of like combining both of those. So it's going to say, if a student is not good at math, then he or she is not in calculus. Okay, and that, the contrapositive, is always going to match the same meaning as the if-then. In the if-then, we said if you're in calculus, you are good at math. And so if you're not good at math, then you can't be taking calculus, because if you were in calculus, you would be good at math. So the contrapositive is always going to match the same meaning as the if-then, so this is going to be true. If the if-then is true, the contrapositive is true. All right, we have a whole nother set, so we'll start with number 19. A poet is a writer. So a poet comes first there, so we can say, if you are a poet, then you are a writer. All right, and I think if you are a poet, then you are a writer. We would have to agree that that's true, because writing poetry is a type of writing, so true. How about the converse? If you are a writer, then you are a poet. That's not necessarily true. You could just be a writer of good stories, but you never write poems. So we're going to say that is false. So you just reverse the if-then in order to get the inverse, the converse, excuse me. For the inverse, which is next, we want to leave the if-then in the same order, but put negatives in. So it's going to be, if you are not a poet, then you are not a writer. And the inverse always has the same meaning as the converse. So if the converse is false, the inverse is also going to be false. It's just kind of stating the converse in a different way. Lastly, the contrapositive. This is going to take the original if-then and reverse the order and also negate. So we're going to put being a writer first, then being a poet, but we're going to say if you're not a writer, then you're not a poet. And so that's going to be true, first of all, because if you just think about it, if you're not a writer, so you don't do any kind of writing, well then yeah, you can't be a poet. Another reason why we know it's true is because the contrapositive always matches the meaning of the original if-then form. So if the if-then is true, the contrapositive is true. If the if-then were actually false, the contrapositive would be false also. All right, next up we have two laws that we use. The first is called the law of detachment. And basically this is where we give you a kind of rule, and then we get specific and ask you to apply that rule. So here's just a general rule. If the light is on, then someone is home. All right, so we're going to assume that that if-then statement is true. If the light is on, then someone is home. All right, now we're being told the light is on. So the directions say make a valid conclusion. So all you have to say here is someone is home. It's just using what you've been given to tell what the situation is. All right, the next one, if you do your geometry homework, you can take the test. You have done your geometry homework. Well, then you can take the test. All right, the law of syllogism is a little bit different for 25 and 26. This is where we're basically going to combine two if-then statements. Notice in the law of detachment, we didn't have two if-then statements. We had a single if-then statement and then a hypothesis. So, look at 25. If Celia practices all week, she can play in Saturday's soccer game. If she plays in Saturday's soccer game, the team will win. So we're going to kind of combine those to just say the first thing that happens and the last thing. So if Celia practices all week, then what's the last thing that will happen because of that? Then the team will win. And you're just kind of leaving out the middle part of that. We're not saying that it's not true, we're just not saying it, we're just leaving it out. Here's a mathematical example, number 26. If 5x equals 65, then x equals 13. If x equals 13, then x squared equals 169. So it's kind of like if event A leads to event B, and event B leads to event C, we're summarizing it by saying, you know what, A eventually causes C to happen. So in this case, the first thing that happens is if 5x equals 65, then what's the last thing to happen here? X squared equals 169. Alright, so that covers the first half of Chapter 2. The last half of Chapter 2 is all about proofs, and we start with algebra proofs. This is solving an algebra equation, something you already know how to do, but what we learned is how to set it up as a proof and give reasons. So, number 27, we start off with 3x minus 7 equals 20. What's our reason for that? It's given. It was just already there. Alright, now to solve this, I would add 7 to both sides. And the reason why I'm allowed to do that is the addition property. And you can abbreviate if you want. And so when I add 7, the 7's will go away on the left side, and I'll have 3x equals 27. So it's because of the addition property that I could do that. Next, I would divide both sides by 3 and get x equals 9. That's my answer. And it's the division property that allows us to do that. So you're just solving the equation like you normally would, but you're giving a reason for each one. And you don't have to memorize all of these reasons, although addition, division, that's not too hard to remember. Remember, you can use the postulates, theorems, formulas, properties packet that you got in class and that you'll be given on the test. Number 28, all right. So this original statement was just given. From there, I would subtract 5 from both sides. So that's the subtraction property. And when you do that, you get 2x equals negative 22. So that was the subtraction property that helped me get that. Then I would divide by 2. And it looks like here our answer is x equals negative 11. And that was the division property. All right. And on to number 29. So this is given. Sometimes you just want to dive right into the problem and you forget to put why that original statement's there, and it's there because it was given. And so what I would do next, I think what most people do, is they would distribute this 4. And so they'd have 4x plus 12 equals 28. And so what allows us to do that? Well, the distributive property. Okay. From there, I would subtract 12. So you get 4x equals, what's 28 minus 12? 16. So that's the subtraction property. And then lastly, I would divide by 4. And we get our answer of x equals 4. And that would be the division property. All right. So here we have a couple proofs, and on the test you will have 2 proofs. One of them is going to say write a 2-column proof. I want to make sure you know how to do that, so let's just set that up with statements and reasons. Just a regular 2-column proof. And the first thing we usually do is state the given, so angle 2 is congruent to angle 3. Alright, maybe I'll mark that on my diagram, angle 2 congruent to angle 3. And in the end, I need to prove that angle 1 is congruent to angle 4. So maybe you have an idea of how to do that, maybe you don't. What I would suggest, if you don't really know where to go, is try to just think of things about what you're given that are true. So when I look at this diagram, I think, well, angle 1 and angle 2 are vertical angles, and that means they're congruent. So I'm going to say angle 1 is congruent to angle 2 because they're vertical angles. And you can put that, or we did actually learn that this has a specific name. This is theorem 2.6. I don't have that memorized. I just looked it up on the sheet that you're allowed to use. You know, while I'm at it, I might as well say the same thing about 3 and 4. I know those are vertical angles too, so angle 3 is congruent to angle 4. You can put them in the same box if you want, or you can make them 2 separate steps. Okay, well now when I just look at my diagram, I can see all 4 of these are congruent to each other, and so that includes 1 and 4, which is what I'm trying to prove. So I think we have enough information to go to the end here. Angle 1 is congruent to angle 4, but what's our reason? Well, if we're saying that these are all congruent to each other, they're all like equal measures, then what we're doing is we're replacing one with another. It's like we're taking our original statement of 2 is congruent to 3, and instead of saying 2, I'm going to say 1 because I know 1 and 2 are congruent. And on the right side, instead of saying 3, I'm going to say 4. I'm replacing 3 with 4. So this would be the substitution property that allows us to do that. Anytime you're replacing, that's substitution. Sometimes substitution and transitive are very similar, but here we really should not use transitive because look, we have 4 separate angles. The transitive property is always about 3 angles at a time. So there it is. Okay, the last one here, number 31. Write a 2-column or other type of proof. So if you wanted to go with a paragraph proof or a flow proof, you could do that. I'm probably just going to stick with the regular 2-column proof. So I'll go ahead and set it up. Statements, reasons. Okay, and we'll go ahead and state all the given stuff. HI equals 9. I'm going to mark that on my diagram also. IJ equals 9. Alright, there's that. And segment IJ is congruent to segment JH. So segment IJ congruent to segment JH. And all of that is given. And I need to prove that HI is congruent to JH. HI congruent to JH. Well, when I look at this diagram, it seems to me like these are all going to be 9, because these two are 9, and these two are congruent. So this has to be 9 also. So yeah, these would be congruent. It's just a matter of getting there. So let's see here. There's a few different ways you could go about this proof. One way that occurs to me is to take the statement I just wrote down about IJ and JH, and if they're congruent, that means they have equal distances. So I'm going to say distance IJ must equal distance JH. And how do I know that? Well, that's what congruence means. So the definition of congruent segments is that they have equal distances. Alright, now let's use some substitution, and here's how I'm going to use substitution. I know that IJ equals 9, so instead of writing IJ, I'm going to repeat what I just wrote, except instead of writing IJ, I'm going to write a 9. So it's going to say 9 equals JH, and so that was substitution that allowed me to do that. So now if you look what I have JH equals 9, HI equals 9, IJ equals 9. I've proved that they're all 9, and I know you probably just knew that from looking at it, but you got to prove it in an organized step-by-step manner. So now I can do another replacement. If JH equals 9 and HI also equals 9, I can replace one for the other. And this, you could either use the transitive property, because it's like you're saying HI equals 9 and 9 equals JH, therefore HI equals JH. Or you could substitute, either one. I'll just say it's the transitive property. And I'm going to replace 9 with HI. And so I'll have HI equals JH, which is almost what we want in the end. What we want in the end is HI is congruent to JH. So that's just going to be one more step where I make that equals. I'm just going to make this equals statement into a congruence statement. Although they kind of mean the same thing, on paper they are written differently, so it's another step. So how do I know that these are congruent? Well, again, that's the definition of congruence, that they have equal segments. So now we have proved that. There's probably a bunch of different ways that you could prove this. This is just the way that I chose.